Hey guys, welcome back to Bicen Maths. This is the second part of the video in how to integrate anything in A-level maths. If you haven't watched the first part, I go through all the different techniques and how you should spot them. What I'm going to be doing in this video though, is I'm going to go through all 24 of the questions and I'm going to work them out so you can see if you get the same answer as I do. Okay, so this was what we looked at before, all of these different techniques. We decided for these 24 questions, these were the different methods that we were going to be using. I've also made all of these questions available in my Bicen Maths Google Drive as a PDF so that you can print them off and have a go as well. And I've also got some questions by another mathematician called Dr. Tim Honeywell, and he's done some amazing integration questions that you can use for extra practice at the end of this as well. And they're all in the Bicen Maths Google Drive under how to integrate anything. Okay, so let's get going with these questions. The first one that we've got here is sec squared x. And I said for this one, this is actually just a standard result. So this should be pretty easy. We know that the thing that differentiates to sec squared x is just going to be tan x plus c. So that's just a standard result for this one. Question 2 that we've got here, we said that this one is actually just a standard result as well. And because it's a standard result, we can just go straight in. There may need to be some scaling as well. So here I can see that it's something to the power of 5. So I know what I would usually do is I would raise it to the power of 6 instead. So what I often do is I check by differentiating this and then see how I need to scale it. So over here I'm going to differentiate it. 3x plus 2 to the power of 6 would differentiate to 6, 3x plus 2 to the power of 5, but I would also multiply by the derivative of this, which is 3. So I've got this extra 18 at the beginning, so to scale that, I'm going to have an 18th at the beginning. So it's going to be an 18th, 3x plus 2 to the power of 6 plus c. Okay, question 3 that we had like this. This one we recognized was a reverse chain rule because this beginning part, x, is related to the derivative of this part that we've got here. Now my tip for this one would be to rewrite this 1 plus x squared square rooted as 1 plus x squared square rooted as the index instead. Now, for this kind of thing, I'm just going to be concentrating on integrating this main bit because this part from the reverse chain rule has kind of come up because of the derivative of this section. So what I'm going to do is I know it's going to be 1 plus x squared to the power of 3 over 2. I'm going to increase that power from a half to 3 over 2. And then over here, I'm going to differentiate it and I'm going to see how I need to scale it. So first of all, to differentiate this, I'd have the 3 over 2, 1 plus x squared to the half by decreasing the power, but I'd also need to multiply by the derivative of this, which is 2x. So you can see in this bit, the 2's would cancel, and I would just be left with a 3x that I've got here. So to scale it, I need to get rid of that 3 by doing a third here. So my answer is a third 1 plus x squared to the power of 3 over 2 plus c. Question 4 that we've got. This one we had a look at before and we said this was a standard kind of result. This is because when we look at this kind of function that we've got here, I recognize the double angle formula in both the numerator and the denominator. So first of all, I'm going to take this a little bit slower. The numerator is 2 times 2 sine x cos x, and we know what 2 sine x cos x is. And if I factorize the bottom by taking out a factor of 4, I get 1 minus 2 sine squared x. And we can recognize what 1 minus 2 sine squared x is as well. So here we've got 2 multiplied by sine 2x over 4 multiplied by cos 2x. That's because 1 minus 2 sine squared x is cos 2x. Now the 2 over 4 that we've got here is just going to simplify to a half, and the sine over cos is going to go to a tan 2x dx. Now you'll notice I've included here, this is from the formula book, because we know how to integrate tan 2x using the formula book, so we can actually just apply this straight away. We'll leave the quarter that's already there, and we're also now going to integrate tan 2x using this, so it's going to be a half ln of sec 2x plus c. Simplifying that half times a half, and we have a quarter ln sec 2x plus c. Now, if you ever wanted to check these things, you can always differentiate your answer and see if you go back towards the thing that you integrated to begin with. Okay, let's keep going. Question 5. I wonder if you can remember what this one was from the first video. This one is not reverse chain rule. This is an example of one which is going to be by parts. So in this case, we're going to select the polynomial as the u term, so it's going to be 2x, which means that the sine 3x minus 1 is going to be the v dash term. So u will differentiate to 2, And sine of 3x minus 1 is going to integrate to, well, we know that cos is going to go to minus sine, so it's going to be a cos of 3x minus 1. We're going to have the negative to counteract the fact that it's a negative, and we're going to have the third to counteract the 3x that we've got in here. Just check, does that work? Minus the third cos 3x minus 1, yep, that will differentiate to sine of 3x minus 1. Now, applying the formula here, we've already used this pair. So the next bit we have are these two being multiplied, which is going to be minus 2/3 x cos of 3x minus 1. And then we're going to be subtracting the integral of these two things. Now, if I'm subtracting a negative, it is going to become a positive integration of 2/3 cos of 3x minus 1. And I'll squeeze that dx in there as well. So we have minus 2/3 x cos of 3x minus 1. And then the integration of this bit that we've got here is just a kind of standard result and some scaling. So I know that there's going to be a sine of 3x minus 1 because sine differentiates to cos. And I'm going to counter that extra 3 inside here by dividing by 3. So it's going to be 2/9 sine of 3x minus 1. Don't forget that plus c, okay? So I'm just going to double check that's what I had over here. Yep, that's the same answer. Okay, so question 6 that we've got. I wonder if you can remember what this one was. This is a classic example of just splitting the numerator. So when I split this, I'm going to have x over the square root of x minus 1 over the square root of x. Need brackets now because it's a two-term expression, and that's going to be integrated with respect to x. So this in index form is x over x to the half minus 1 over x to the half. Let's keep simplifying this. X over x to the half is just going to be x to the half, and 1 over x to the half is going to be x to the minus a half with respect to x. So this is just a standard result now. I'm going to increase that power to 3 over 2, and then I'll have it as 2/3. I'm going to increase this power to a half, and I'm going to multiply by the reciprocal of that, which is the 2 that we've got there. So it's a split the numerator and then a standard result kind of question. Number 7 that we've got here, I wonder if you can remember what we said this one is. When I look at this, I see that sine x is related to this function that's inside the function. So I know that this one is going to be a reverse chain rule that we've got. So I know with e to the x functions, this is the main body of the function. The thing that will integrate to is just going to be e to the cos x. Now, if you think about how e to the cos x will differentiate, you would get minus sine x e to the cos x using the chain rule for differentiation there. So I've nearly got the exact thing I wanted, apart from there should be a negative to flip it back to positive. So it is minus e to the cos x plus c. Question 8. This one, I think we remember this as algebraic division because it's a top-heavy or an improper kind of fraction. So I'm going to do it down here. I'm going to do x plus 1 divided by x minus 1. Well, x divided by x is just going to give me 1, so let's multiply that. So that's x minus 1. When I subtract these, I have 1 minus minus 1, which is just 2. So this is the same as 1 whole 1, which came from this bit up here, and a remainder of 2. Now, the remainder of positive 2 is going to be over x minus 1, like this. If you wanted to check this, you could actually just take these two fractions and add them together. So 1 is just x minus 1 over x minus 1, plus 2 over x minus 1, and pretty clearly you can see this numerator is going to be x plus 1, and the denominator will remain as x minus 1, so it still works. Now we can just integrate this. 1 integrates to x, and the next part that we're going to have is going to be 2 lots of ln of x minus 1 plus c at the end. Okay, question 9 that we've got here. This one is a reverse chain rule because this bit inside here will differentiate to something similar to the bit outside the front. I like to rewrite this so that it's x brackets x squared plus 1 to the half, and this is the function I'm concentrating on integrating, and it's something to the power of a half, so I know I'm just going to be increasing that power. I'm going to be increasing that power to 3 over 2. Now, somewhere else on the page, I'm going to differentiate this so that I can see what it needs scaling to go with it. Some people can do this in their head. I'm just taking it easy and going a slightly longer route. So when I differentiate this, I would pull the power down, I would reduce the power by 1, and I would also multiply by the derivative of this bit. So I'm also going to be multiplying by 2x. So the 2's would cancel, and what I'd be left with is a 3x outside the front. I only wanted an x outside the front, so I'm going to have to third it to get the correct kind of scale that I've got there for question 9. Now I'm going to have a look at question 10. This was an example. It's pretty obvious when you look at the question. This is an example of a partial fractions. So I'm going to perform partial fractions on this. I've got my 3x plus 2, x plus 1, x minus 2. I'm going to split that into an a over an x plus 1 plus a b over an x minus 2. So 3x plus 2 is equal to a x minus 2 plus b x plus 1. I'm going to start off by finding out what b is by subbing in that x equals 2. So 3 times 2 is 6, plus 2 is 8. The a part is going to disappear, and I just get that with 3b over here. So b is equal to 8/3. Now, if x is equal to minus 1, I can find out what a is. So that would be minus 3 plus 2, which is minus 1. And then I get minus 1 minus 2 is minus 3a, meaning that a is 1/3. So my tip for how we would integrate this is I would rewrite it with the a literally just staying up in the numerator. So I've got 1/3 of x plus 1. And then b is 8/3. I'm just going to keep it up in the numerator like that, a fraction within a fraction, x minus 2 with respect to x. Because when I integrate this, it's just going to be 1/3 ln of x plus 1. So it's nice and easy. 1/3 of ln x plus 1 plus the next bit is just going to be 8/3 of ln x minus 2, just some standard results that you've got there. I'm not going to try and combine these or anything, but the question may want you to do that as well. Okay, let's have a look now at question 11. Hopefully you can remember from before and you can spot this. It's just going to be a split the numerator kind of question because there's just a single term in the numerator. So that's x over x plus 1 over x, which is going to be integrated with respect to x. X over x is just 1. So we can now integrate this expression that we've got here. Obviously 1 integrates to x and 1 over x integrates to ln x. And obviously there's going to be a plus c at the end there. Okay, question 12. This one was a special case. Now I want to see if you can remember out of the different techniques, what should we use to integrate ln x? It is not a standard result. Can't do any of those other bits. The one you have to use is by parts. Now for this one with by parts, I said that you usually take the polynomial as priority for you, but ln x takes top priority. Now there's secretly a 1 here, isn't there? So that means that v dash is actually 1, meaning v when you integrate 1 is x, and u dash differentiates to 1 over x. So we've already used this pairing. The first bit we get is uv, which is going to be x ln x, and then we're going to subtract the integral of v multiplied by u dash. So that's v multiplied by u dash with respect to x. So that is x ln x minus the integral of x over x. Well, x over x is just going to be 1. And so we have x ln x minus x plus c. Now this looks pretty weird as something quite simple to integrate to this. What I would recommend you trying now is differentiating this and seeing that it goes back to ln x. It's pretty cool actually. All of these you can differentiate and see if you go back to the same bit. Okay, 13. So this one, I'm not sure if you can remember this, but this one we said was a reverse chain rule. Probably one of the hardest ones to spot here, I think. If I rewrite this, it might be easier for us to spot why it's the reverse chain rule. So this is 1 over x, and then I'm going to put ln x in brackets with a power of half, rewriting the root as a power of half here. So we've got this function inside the square root function, and the derivative of this function is 1 over x, which makes me think I'm just going to concentrate on this ln x to the half and integrate that in the way that I would expect. Now, I would expect something to the power of a half to bump up that power by 1 to 3 over 2. So I'm just going to differentiate this and see what happens so that I can scale it and perform the reverse chain rule on here. So what I would do is I would pull down the power, I would reduce the power by 1, and I would also multiply by the derivative of the thing that's inside the brackets, which is ln x, so it's 1 over x. So looks like I've nearly got exactly what I wanted here. I've got the 1 over x and the ln x to the half, but I've got a 3 over 2. So to counteract a 3 over 2, I'm going to have a 2 over 3. So kind of weird for this one, but it does just go to a 2 over 3 ln x to the power of 3 over 2 plus c. Okay, question 14 that we've got here. When you look through the list of things that we've got, it doesn't appear that we can use any of these. So we do go for our last resort. Now, when I say last resort, it's only because I think substitution is one of the hardest ones. You can do substitution instead of reverse chain rule, for example. I just prefer to do reverse chain rule if we can, because it's so much quicker. This one is going to need to be substitution. Now, you could try doing like u being equal to e to the x. It's not going to do anything. It's not really going to change what's going on with your function. So I like to try the whole denominator. So I get u equals 1 plus e to the x. Okay, we're going to differentiate this so that we can find out what dx is. So this is just going to differentiate to e to the x. So that's du by dx equals, well, e to the x, if you look at this top line that we've got here, it's just u minus 1. So I can replace it with u minus 1. So we get 1 over u minus 1 du is equal to dx. So I can now actually go and do that substitution. So it's going to be 1 over u, and then dx is 1 over u minus 1 du. So I've transformed it now into just a completely u kind of one. So what I've got is I've got 1 over u minus 1 du. Now this thing that we've got is going to need to have some partial fractions happening on it. So I'm going to do this partial fractions and see if I can squeeze it in on the left hand side. So I have 1 over u minus 1 is going to be a over u plus b over u minus 1. So first of all, we get 1 then equals a u minus 1 plus b, plus b u. Let's let u equal 1 to start with, then we get 1 equals b. Then let's let u equal 0. We get 1 equals minus a, so a equals minus 1. Okay, if I'm going too quick through some of these things, then you might need to check out some of those other skills like partial fractions and some of my other integration videos. So I'm going to now rewrite this in partial fractions. So a over u, I'm actually going to start with the b over u minus 1 because b is positive and a is negative, and I like to start with the positives. So we get 1 over u minus 1, and then a is minus 1, so that's minus 1 over u du. So I can just now integrate this. This is just some standard functions. So it's going to be the ln of u minus 1 minus the ln of u plus c. Don't forget to replace it with what we originally had. So let's just quickly think what u minus 1 is. Well, u minus 1 is just going to be e to the x. So this is the ln of e to the x. I don't really need the modular signs here because e to the x is always positive, minus the ln of u, which is 1 plus e to the x. Again, I probably don't need those modular signs because 1 plus e to the x is always going to be positive. I would do one final bit of simplifying, which is that ln of e to the x is just x. So it's x minus ln of 1 plus e to the x plus c. A lot more work for a substitution kind of question, so they're usually quite a demanding one. Oops, never highlighted that it was substitution. Let's continue and have a look at 15. Now, I hope you can tell which one this is, even if you don't remember it from the first part of the video, but this is by parts because we've kind of got like a combo of two things here. So the priority is going to be that u this time is going to be x, meaning that v dash is going to be sec squared x. X differentiates to 1, sec squared x integrates to tan x, and that's a standard result. So we've already used this pair. The first pair that comes up is going to be the uv, so that's going to be x tan x. And then the last bit is we're going to be subtracting the integral of tan x dx. Now remember earlier on, I said that the integral of tan x is just in the formula book, and it was ln of sec x plus c. If you wanted to, because this is a subtract ln of sec x, that's saying it's a sec x to the power of minus 1, you could, if you wanted to, rewrite this as an ln of cos x with a plus, but I'm happy with either of these two answers that we've got here. Again, check this out, differentiate this one and see if you do go back to x sec squared x for question 15. So let's try 16 that we've got here. Now 16 is an example of a reverse chain rule. It's a reverse chain rule because when you look at the numerator, it's clearly related to the denominator that we've got, the derivative of the denominator. Now that kind of function where the numerator is related to the derivative of the denominator is the kind of thing that is going to integrate to an ln function, okay? So we're going to say that I think this is going to integrate to an ln of 2x squared minus 3. I'm going to, over here, differentiate it and see how I might need to scale it to make it look right. So it's going to have, the denominator is going to remain 2x squared minus 3, and the numerator is going to be the derivative of 2x squared minus 3, because that's how ln functions differentiate, and it's going to be 4x. So we've got 4x over 2x squared minus 3. We wanted it to be a 2x. So we're going to have to half that to go from the 4 to the 2. And don't forget that plus c that we've got at the end there. Question 17 that we've got. Now, this one also is an example of a reverse chain rule because the 2x is related to the derivative of this, this denominator. Now, the worst mistake I see people making here is they go straight in and say, oh, well, it must be an ln of x squared minus 3 squared. They just think that anything that's a fraction is going to go to ln. But that's not true. It's only if the denominator is of like power 1 that it will go up to an ln function. In this one, the denominator is a squared kind of function. So you may find it easier if I write it like this instead, as 2x x squared minus 3 to the minus 2. You might then recognize how you integrate these kinds of functions, because it's kind of like a standard one that you would have done quite early on. All you need to do is just increase the power by 1. That's why it works with ln functions. When you try and increase the power, with functions like this one, this is to the power of minus 1. If you increase it from minus 1 to 0, things go weird. That's why this ln function comes in. So we're going to do the same thing for the reverse chain rule. I am going to differentiate this and then see how I need to scale it. So I've got x squared minus 3 to the minus 1. When I differentiate this, I'll pull down the power, so that's minus x squared minus 3, and I'm going to reduce that power by 1. And I'm also going to multiply by the derivative of this thing, which is 2x. So it's actually nearly exactly what I wanted it to be up here, apart from there is a negative. So to counteract that negative, I'm going to put a negative in it to flip it back to a positive. Okay, we're nearly there. We're coming on to question 18. Now this one, I know that this is a by parts question, but one of the things I want you to look out for when by parts is useful, it's when the two kinds of functions that you've got here feel really different to each other. Earlier on we had one that was trigonometry and a polynomial. Here we've got a polynomial and an exponential. It's often when there's like a clash of two functions that this can happen. Not always, but this is often the best time that by parts will happen. Now, I'm not sure if you remember from before, but this is actually a by parts twice question. So I'm going to see if I can squeeze all of this in. I will let the x squared take priority for being the u value. So that means that v dash is e to the 3x. U will differentiate to 2x, and v dash will integrate to a third e to the 3x. So the first bit we'll get, we've already used that pairing. We'll have the third x squared e to the 3x minus the integral of this pair, which is going to be 2/3 x e to the 3x dx. Now you'll see why I'm talking about integration by parts twice, because this thing also requires integration by parts. So I'm going to do that underneath. This time I'm going to let u be 2/3 x. V dash is e to the 3x. We integrated this before and we got a third e to the 3x. Nice and easy. It's just going to differentiate to 2/3. So we've already got that pairing from the question. The first one we're going to have is this. So I'll rewrite that third x squared e to the 3x from the previous one. I'm going to do some big brackets here. So uv is going to be 2/3 x times 1/3 e to the 3x. These two things multiplying. The number will be 2/9. There will be x e to the 3x. And then we're going to subtract those two being multiplied, being integrated. So that is going to be 2/9 e to the 3x dx. So rewriting that first term, a third x squared e to the 3x minus 2/9 x e to the 3x plus the integral. The reason it's a plus is because there's a negative and a negative. the integral of this. And this is just going to be a standard result plus some scaling. So I know it's going to be an e to the 3x, and it's already a 2/9, but I'm going to have to scale it by a third. So it's going to be a 2/27. A third of 2/9 is 2/27 plus c. I kind of like this question because you can see some patterns here. We've got an x squared, then an x, and then no x term here. So you've kind of got some patterns as it goes. And I would challenge you to differentiate this and see that it goes back to x squared e to the 3x. It's kind of nice to see how that one works. So this was an example of biparts, but in particular, it was biparts twice. Okay, question 19 that we've got here. Hopefully you can remember what this one was, but I can see there's a clear relationship between them that makes it a reverse chain rule. So sometimes I like to rewrite this so that it is sine x cos x to the power of 3. So clearly, when you've got something like this, where the derivative of this function that's inside the cubing function is related to the function outside the front, that's what triggers you thinking it's a reverse chain rule question. So I know I'm going to want to increase the power on this thing so that it's no longer cubed, but I think it's going to be to the power of 4. So I'm going to differentiate cos x to the power of 4 and see what we get. Well, I'd pull down the power, I would reduce the power by 1, and I would multiply by the derivative of what was inside, which is cos x, and cos x differentiates to minus sine x. So it looks like I've nearly got this thing at the top. I've got the sine x and the cos cubed x. I've got here the sine x and the cos cubed x, but I've also got a negative and a 4. So I'm going to counteract that by a negative and a quarter. The negative to make it become positive, and the quarter to make it just have that coefficient of 1 that is here. And of course, we've got plus c. You'd probably rewrite this, though, as a quarter cos to the power of 4x plus c, like this, because we normally put the powers in that place for trig. Okay, 20 that we've got here. We want to do an integration of tan squared. Now, this one is a standard result, but it's not just a standard result. It's a standard result that needs a bit of manipulation here. So I'm hoping you know your trig identities. This one is to do with the Pythagorean one. We know that 1 plus tan squared x is sec squared x. This we don't know how to integrate. This we do know how to integrate. So we can say that tan squared x is sec squared x minus 1. So I can rewrite this as sec squared x minus 1 dx. And I know that the integral of sec squared x is just tan x, and I know that the integral of 1 is just x. So we get tan x minus x plus c. Okay, 4 more questions to go. So for this one, it's definitely not going to be like a reverse chain rule because the numerator isn't related to the derivative of the denominator. I can't split the numerator because there's 2 things in the denominator, no partial fractions. I'm going to do algebraic division here. Now you may think substitution is a good option, but I think it's going to be a lot more work. So we're going to do algebraic division. There's lots of different ways you could do this. This is just the way that I know my students will have done algebraic division. So I'm going to be doing x squared, and I'm going to be dividing it by x plus 1. So first of all, x squared divided by x is just going to be x. So I then have, multiplying this by this, I get x squared plus x. And when I do that subtraction, I'm going to have nothing minus x, which is just minus x. Now I'm going to do minus x divided by x plus 1, which is going to be minus 1. So I'll multiply through by minus 1, so I get a minus x minus 1. And when I subtract these, I get nothing minus minus 1, which is 1. So this means that the x squared over x plus 1, there's x minus 1 and a remainder of 1. So that is going to be x minus 1 and a remainder of positive 1. So that's going to be over the same thing that it was being divided by. Now, if you want to see why this thing here works, you could actually add these. So I'm going to put these all as a common denominator of x plus 1. So I would have x would need to go with an x plus 1. The minus 1 would need to have an x plus 1, and the 1 is already over the x plus 1 like this. Simplifying that numerator, I've got x squared plus x minus 1 plus 1. I don't think I have expanded that bit correctly. Oh no, I have, that's good. X squared, oh no, I expanded the brackets wrong at the beginning. This should have been x squared plus x. So you can see what happens here. The x and the minus x cancel, the minus 1 and the 1 cancels, and you are indeed left with x squared over x plus 1, which is what was happening. So that's why we're allowed to perform that algebraic division that we've got there. People might do that in other ways. This is just the way that my students have learnt. So now I've got it looking like this. I can just integrate all of these bits separately. So x integrates to a half x squared. 1 will integrate to x, and 1 over x plus 1 is ln of x plus 1. Don't forget that plus c that we have at the end. And again, you could differentiate this and see if you come up with this when you confirm and when you put everything all back together. 3 more questions to go. Oh, I didn't say this one was algebraic division, so I'd like to highlight which it was. We're going to try question 2 that we've got here. Now, question 22 that we've got here. So this one looks kind of tricky, right? Because the numerator is not related to the derivative of the denominator. So there's a couple of different options you could do for this one. I think you could manipulate it into a by parts kind of question, but actually I would probably lean towards doing a substitution for this. If you wanted to do by parts, you would rewrite it so that it was like an x plus 1 to the minus a half, and you could do by parts on that. But I'm going to try this as a substitution. So with it as a substitution, you could either say that u is the square root of x plus 1, or you could even try that u squared is equal to, no, I would just go with u equals the square root of x plus 1. You could try that u is x plus 1 like this if you wanted to. That's what I was going to say. But I'm going to go with that one. So first of all, I would probably rewrite this as x plus 1 to the half. I'm going to square both sides so that u squared is equal to x plus 1, meaning that u squared minus 1 is just equal to x. Now we also need to find out what du dx is. So I am going to take that top bit. In fact, I'll take this second line that I've got here and I'm going to differentiate it. So du dx is going to be a half x plus 1 to the minus a half, meaning that I could say that this is actually 1 over 2 root x plus 1. So I can now multiply that through and I get 2 root x plus 1 du is equal to dx. I've multiplied by the dx here, put it up to the other side, and I've multiplied by the 2 root x plus 1 and put it up here. So I can now go straight in with the substitution. We know that x is equal to u squared minus 1, and we've got on the denominator u. I'm going to be multiplying by 2 root x plus 1 du. Now root x plus 1 is u, so instead of writing 2 root x plus 1, I can write 2 u. So that's 2u, and that is all du. Now what you'll notice here is this u in the denominator is going to cancel with this u in the numerator up here, meaning this question suddenly becomes quite a lot more simple. It's just 2u squared minus 2 being integrated with respect to u. So I'm going to just go straight in. I'm going to increase that power and divide by 3, and I'm going to have that as a 2u from this integration that we've got. Now what you need to make sure that you do is you sub everything back in so that it's in terms of x. So it's going to be 2 over 3. Now u is x plus 1 to the power of a half, and it's being cubed, so it's going to be x plus 1 to the power of 3 over 2, and we've got minus 2 brackets x plus 1 to the half plus c. Like I said, you could have tried this with by parts. My mind kind of goes to substitution with this, but you can see how much more demanding substitution is than some of those other methods that we've got. Okay, 2 more questions. Question 23 here. I wonder if you can remember which this is. So almost this looks like it could have been a reverse chain rule. However, the denominator would differentiate to 2x plus 3, not 2x minus 1. So you can't do the reverse chain rule here. This one is going to be, you might think it's algebraic division, but actually it could be partial fractions, because 2x minus 1 over x squared plus 3x plus 2, x squared plus 3x plus 2 factorizes to x plus 2, x plus 1. So I know that it can be written as a over x plus 2 plus b over x plus 1, meaning we have 2x minus 1 equals a brackets x plus 1 plus b brackets x plus 2. And I'm going to start off by letting x equal minus 1. So on the left hand side I have minus 5, and on the right hand side I have 2 minus 1 is 1. I just have b, so b is minus 5. And I'm also going to let x equal minus 2, so that I then get minus, what's that, minus 4, minus 5 again. Wait, hang on a second. I think I've done the first side wrong. I think actually this should have just been -3, not -5. This is -3, silly me. So we get -5 equals -a, meaning that a is equal to 5 on that bit of partial fractions. So that means this is going to be integrating as 5 over x plus 2, that's my a over x plus 2, minus b, which is -3 over x plus 1 dx. And then we've got a couple of standard results here. That's just going to be 5 ln of x plus 2 minus 3 ln of x plus 1 plus c. Now, if you wanted to, you could combine these things together, but I'm not going to be having these things combined. I'm just going to leave them as the way that they are there. Okay, so we're on the very, very last question now, question 24. This one is just a standard result, but kind of like a special case that I'd like you to try and memorize for this. This one comes from the rearranged double angle formula, where sine squared x we know is just a half minus a half cos 2x. I would ask you to memorize this because it's quite a common kind of integration question. But in case you don't know where this has come from, this has come from the fact that cos 2x, you should know this one for sure, is 1 minus 2 sine squared x. When this gets rearranged, 2 sine squared x is 1 minus cos 2x. In other words, sine squared x, when I divide everything by 2, is a half minus a half cos 2x. So instead of integrating sine squared x, which can't be done in that form, I'm going to write it as a half minus a half cos 2x with respect to x. The half is going to integrate to a half x. I know that this is going to go to a sine of 2x, and it's going to be minus a quarter to counteract that 2 that we've got inside there, plus c. I often get a question, why can't I, with sine squared x, why can't I integrate it and just get a third sine cubed x? Why can't I just increase the power by 1 and divide by that new power? Well, there's the challenge for you. Differentiate this. If you differentiate this, I can guarantee that you will not get sine squared x. You will not get sine squared x. Try it out and see why. If you do get it, it's because you don't understand the chain rule, so you might need to go back and revisit some of your differentiation stuff. So if you liked this, I've put the worksheet for you guys in the Bicen Maths Google Drive, as well as some questions that were created by Dr. Tim Honeywell. They are called Lots of Lovely Integrals. He's also done, as well as 100 questions, there are the full solutions for all of them, as well as the short answers as well, so that you can get loads and loads of practice on this. This is often seen as quite a difficult area, but with practice, it can become a really strong area for you. If you like this video, please do drop it a thumbs up, and make sure you're subscribed to my channel if this is the kind of stuff that you think would be useful. Good luck with any exams that you've got coming up.